We're going to do something similar, but at the same time, something a little bit different. So far, when it comes to derivatives, we have only kind of looked at polynomials, right? Polynomials like x squared or x squared plus 1 cubed, or when this guy is in the denominator. Basically, we've looked at rational functions, and we have looked at the other guy, which is just normal polynomials. For polynomials, it's pretty easy. If y is I don't know, like k times e to the power of x, y prime will be, you bring that x down, multiply that with this number, if there's a number in front of it, and take 1 away, yeah? So this is a rule for polynomials, or like when you can write x to the power of something, right? When you can turn it into a power, you can use this rule, and it's pretty straightforward. But what if you are unable to do this, right? If you can't write something like this, then you can't use this rule. To understand that, let's look at a function, which is an exponential function. We've done this in the past a while ago. So basically, an exponential function is something that grows exponentially. Like in the beginning, it's very slow, like it doesn't go up as much, but then as the x values go up, the difference between the y values become super big, okay? You ever heard of the term exponential in real life? It just basically means it grows really, really fast. Like, for example, y equals 2 to the power of x is an exponential function. Now, instead of the variable being on the base, like x squared, the variable is in the exponent, okay? That is called an exponential function. At the same time, you have the inverse of an exponential function. Again, if you remember, inverse is simply a function that is flipped over this line, y equals to x line, okay? Instead of like horizontal translation or vertical translation or anything like that, it's a translation along the y equals to x line. For this guy, its inverse function looks like this, which would be y equals to log base 2 of x. Exponential and logarithm, they're inverses of one another, okay? Logarithm grows really quickly in the beginning, but then it falls off later, the opposite of an exponential function. So, like, for example, you want the amount of homework you have in school to follow a log function, and you want the amount of free time you have in life to follow an exponential function, right? More of this, less of that. I guess it depends on the situation. So this is just the basic form of exponential and logarithm functions. One really special exponential function is this guy here, called e to the power of x. Now, e is a constant, like a pi 3.14. E is a constant. This is the natural log number. It's called natural number. Its value is like 2.71 something. Okay, it's a constant. And the inverse of e to the power of x is called ln to the power of x. Ln as in ln. This is called the natural log. Okay. You've seen the log function, which looks like this. Ln of x is the exact same thing, except log of x is the inverse of 10 to the power of x. Ln of x is the inverse of e to the power of x. Okay, this is a constant. Just like 10 was a constant, but this guy just has its own name. You can also say it's log base e of x. They mean the same thing. So if you look at its properties, right? Let's look at an exponential function. Look at this. It starts here and it keeps going all the way. What do you think the domain is of an exponential function? Domain means the possible x values it can take. Are there any restrictions on the domain? If you look at this graph, can x be anything?
Yes.
Yep, so that means there's no restriction. It says right here, the domain of any exponential function is XER. That just means X can be anything on the number line. Now, if you look at the range though, this exponential function will never cross the x-axis. In fact, exponential functions, the base functions anyways, they do not have any x-intercepts. Okay, they do not have any x-intercepts. Can the y ever be 0 for an exponential function?
No.
No, right? You can look at it here as well. Y is never going to be 0. It can be like 0.0001 or something like that, but it'll never be exactly 0. Exponential functions have a y-intercept, right? Y-intercept. It goes through 0, 1, always. Any exponential function. The base function, all these guys, they have a y-intercept at exactly 1 because anything to the power of 0 is a 1, right? Y-intercept is basically the y value when the x value is 0. And since it cannot cross this line, there's something called a horizontal asymptote for exponential functions. There is an invisible barrier. If you look at the ln function, which is just the inverse of this guy, goes this way, everything is the opposite now. Everything is the opposite, okay?
Mhm.
What are the possible x values of a ln or a log function? Are there any restrictions? See, this line never
They
crosses.
can't be negative.
They can't be negative and they also can't be 0. Just like here, y cannot be 0. For the inverse function, x cannot be 0. It's strictly positive, okay?
Mm-hmm.
Over here, x can be anything. What do you think the range is for a natural log function? What are the possible y values? Again, this is going to go infinitely in both directions.
There can be any.
Yeah, y can be anything. So they flip-flop. You look at this. XER from here becomes YER here. Y equals to 0 here becomes x equals to 0 here. And that's a property of inverse function. Inverse function is basically when you swap the x and the y, right? X becomes y and y becomes x. That's the algebraic way of saying it. Graphically, you just flip it on the y equals to x line. So that's just a very brief overview of these guys. Now let's talk about derivatives. Now e to the x is very special. There's a reason why e to the x is very special. It's because the derivative of e to the power of x, okay, let's check this out. The derivative y prime is unlike anything else in maths. There's nothing else that exists, is itself. What that means is that the slope of the tangent for e to the x here, yeah,
Mm-hmm.
is e to the x. The slope of the tangent here for e to the x is e to the x. The slope is going to change depending on the x value, but the slope function, okay, the slope function is itself. And this doesn't happen for anything else. Like 2x squared becomes 4x, right? Sine is going to become cosine. You'll see this later. But e to the x, the derivative, is itself. That's what it says right here. F of x is ex, and this one is ex as well, the derivative. Do you remember the chain rule? Let's do a quick example. Because you're going to have to use the chain rule to do a lot of these questions. So let's say this is y. What is y prime? How do you go about finding y prime? Do you remember that?
Do you do the inside first?
So you look at the bigger picture first. So you're gonna do this bit first. Work from the outside into inside. So you would bring down the 3, okay?
Mm-hmm.
everything inside is gonna stay as it is. And then the 3 is gonna take 1 away, it's gonna become a 2. And then this is a chain rule component. You need to multiply this by the derivative of the bracket. What would that be here? What's the derivative of the bracket?
2x.
Yep. And that's the chain rule component. Okay. This 2x is the chain rule component. If you want the notation, which is going to look a little bit weird, if you have g of f of x like this, where f of x is the inside bit, g is the outside bit. The derivative of g of f of x is g prime of f of x, which is this guy here, just the derivative of the bigger picture, times the derivative of the inside f prime of x. That is the general formula. That's basically the chain rule but you don't have to know this, just understand how it works, okay? This is just for your curiosity. Same thing is gonna happen to any functions that you take a derivative of. Next we're gonna look at e to the power of f of x, okay? The derivative of e to the power of anything is itself. So you're literally gonna rewrite the question that they gave you, but then you're gonna have to multiply by the chain rule component. Okay? Chain rule component. It's gonna be f prime of x, means the derivative of this guy. That's what that means. Cool?
Uh-huh.
So you're gonna rewrite the question, but then you're also gonna multiply by the chain rule component, which is f prime of x. It's gonna be the derivative of the exponent. So here, if that's f of x, what's f prime of x? E to the power of anything, the derivative is itself. Okay, like that. But then you need to multiply this by the chain rule. What do we multiply this by?
3.
Yep, and that's it. You are done. 1 and done. Easy, right? E to the power of x. But then again, like always, it's gonna get more complicated, but that's basically it. But like here, for the second part, you're gonna have to use the product rule. But anyways, let's look at a first. G of x is this guy, right? Wanna have a go at this? What's g prime of x? Again, e to the power of anything, right?
It's the same thing.
It's the same thing. So you're gonna literally just rewrite the question, but then now you gotta multiply this by, so again, this is basically e to the f of x. The derivative is gonna be e to the f of x, exact same thing, times f prime of x, the derivative of the top of the power. What's the derivative of the power?
2x.
Just 2x?
Minus 1.
Minus 1, yep. That's it. Let's look at b. For b, you're gonna have to use product rule. Product rule says this. You have one function multiplying by another function g, f times g. It would be, the derivative would be f prime g plus f g prime. Let's look at it in this context. First, you get f prime. If f is x squared, what's f prime?
2x.
Yep, and then you multiply that by g as it is, right? Plus what? Something times something.
X squared.
Yeah, times.
e to the power of x.
Yeah, e to the power of x. And this one doesn't have an f of x. Well, you can multiply this by a 1, which is the derivative of x, but you don't have to do that bit. And that's it. That is it. How much harder could it possibly get? And you'll see that not that hard. Okay, the f of x is given. What's f prime of x? You're gonna literally rewrite the same thing, right? You're gonna completely rewrite it, and then you're gonna multiply it by the derivative of the power. So it's gonna be 3e to the x squared. 3 is a constant, right? It's not a different function. You don't need to use the product rule. Product rule is only when you have something times something, two different functions.
Times 2x.
Times 2x. And it says find f prime of -1. So f prime of -1, just plug x as -1. E to the -1 squared, that's just a 1. And 2 times -1. So you have -6e. And that's it. Okay?
Mm-hmm.
Is this difficult?
No.
Is this easy for you?
Mm-hmm.
All right, what about this? What do we have to use to find the derivative of this? If you remember. Notice how it's something over something, right?
Mm-hmm.
When you get something over something, it is going to be a quotient rule, which says this. The top one is going to be f, the bottom one is going to be g. Quotient rule says y prime is very, very similar to the product rule, except with a minus in the middle. And then you take the original denominator, g, and then you square it. That is the product rule. Okay? This is f, this is g. So tell me, what's f prime?
E to the power of x times x squared. Minus e to the power of x times 2x.
Yeah? All over what? You take your original g and then you square this. What is x squared squared?
4.
Yeah. And then you simply plug 2 in there. So this is your slope function, right? This is your slope function. We want to find the slope when x is 2. Plug 2 in there. Get e squared times 4 minus e squared times 4 over 16. You can pull out our e squared. Actually, wouldn't that just be 0? They're the exact same things, right? E squared 4, e squared 4, yeah. The slope is 0. The slope is 0, right? What does that mean? What type of a line are we looking at? I'll give you a hint. When the When you plug 2 in there, you get e squared over 4. Yeah?
Mm-hmm.
So a point on the line is 2 comma e squared 4. If the slope is 0, remember, if the slope is 0, it's a straight line. It's a horizontal line. That doesn't have any
Uh-huh.
slope. It's just going to be y equals to whatever the intercept is. Y equals to e squared over 4. Okay?
Mm-hmm.
So basically at 2, looks like there is a turning point for this guy. We can look this up actually. Like, the slope is 0, that means there should be a turning point. What does that even look like? E to the x over x squared. Looks something like this. See at 2, it turns. So when you go and draw a tangent line here, it's gonna be horizontal. And that makes sense, right? The question is, what's the equation of a tangent line? Slope is 0, it's gonna be just y equals to the y-intercept. Okay? Y equals to the y-intercept, that's gonna be the tangent line. So for that graph, it looked wonky, whatever it looked like. It looked something like this. This is gonna be the tangent line, this one right here. What's the equation? Well, y equals to whatever the y-intercept was, e squared over 4. Cool?
Uh-huh.
What did they do? They did the same thing. I don't know. Wait, what? Oh, I don't know what they did. Product rule. Okay, they moved it up. Is this better? I don't think so. This is, I think, if you know how to use the quotient rule, just use the quotient rule. It'll save you some step. But we basically did the same thing, and they got the same number, so it doesn't matter. Okay, here's a communication question. Why can you not use the power rule for derivatives to differentiate y equals to e to the power of x? So like before, we could just bring this 3 down and take 1 away from it, right? This is called the power rule. This is y prime. The question's asking you, why can you not do it for this one? What do you think? What would you say? To use a power rule, you need a number on the exponent, yeah?
Mm-hmm.
Does e to the power of x have a number in the exponent?
No.
No, it doesn't. So you can't use power rule. That is pretty much it. Let's do this one. Okay, so that's y. We're trying to find y prime. Tell me, what is it gonna be?
Is it just the same thing?
Yeah, is that it? Is there anything else to this?
No.
No, there is, right? There is. You always need to multiply it by the derivative of the exponent. It's gonna be the same thing. You don't have to do anything if it's e to the power of x, because the derivative of this is 1, okay? E to the 2x becomes e to the 2x times 2. You always need to multiply the chain rule component. That is it, right? This is part of it, but it's missing the chain rule part. You need to multiply it by the derivative of root x. What is that? So think about it this way, right? We're trying to find the derivative of this. You got to use the power rule. You've got to first rewrite it as x to the power of 1 over 2. Okay, this is just y. We only have y so far. If you use the power rule to differentiate this, what do you get? First, bring the 1 over 2 down, yeah?
Mhm.
And then take 1 over, it's just the power rule, the normal power rule that we do. There you go. This is the derivative of square root of x. So just multiply this by the derivative of square root of x like that. If you want to clean this up, you can throw this guy in the denominator. So you get e to the root x times 1 over 2 root x. Then you can just write this as e to the root x over 2 root x like that. And that would be the final answer. Question for you. Can we cancel out this root x and this root x?
No.
No, you can't. This is in the power, right? This is in the exponent. If this was right here on the same level, yes, you can. The fact that it's in the power means you cannot cancel that out. Here, look at this. It's very simple. The derivative of this is going to be itself. Okay, it's going to be itself. But then you need to multiply this by the derivative of the exponent, the chain rule that's called. What's the derivative of the exponent? We're trying to find the derivative of the exponent. No?
Is it 2x minus 6?
That is it, right? That literally it, and you're done. 2x minus 6. This one you can't even clean this up. That's it. There's nothing else you can't even do. I guess you could multiply this, but that's pointless. This is better. It's just a one-step answer. Okay, it's just a one-step answer. Same thing with this one. It's going to be 2ex cubed times 3x squared. The derivative of x cubed is x squared, yeah? The same thing with this one. The derivative of this d would be e to the minus 3x times negative 3. Negative 3 is the derivative of the exponent. This one you just multiplied by 10. This one you just multiplied by positive 3. You see that?
Mhm.
Alrighty, this one is not going to be very fun. This is where algebra comes into play. If f prime of x is that, sorry, if f of x is that, what's f prime of x? It's going to be itself, right?
Mhm.
You just rewrite the same thing to the negative 1 over x plus 1. But then now you got to multiply this by the derivative of the exponent. This is what we have. How do we go about finding the derivative of this? You can use multiple things.
The quotient rule?
Yeah, quotient rule, right? Exactly. So this is f, this is g. Quotient rule says f prime g minus f g prime over g squared. Ignore the negative sign. That's just going to be on the outside the whole time. F prime is 0, right?
Mhm.
Times g, so that thing is a 0. Minus f is 1. What's g prime? If g is x plus 1, what's g prime?
It's 1.
It's 1. Yep. Then all over g squared, so x plus 1 squared, like that. This right now is a derivative. 0 minus 1 times 1, that's just negative 1. Then you have a negative sign here, a negative sign here. They cancel out or become positive. So basically your chain rule component is this guy here. And you're done. Well, not quite, but that's how you'd find the derivative of the numerator. Okay? Turn it into a quotient rule. It says find f prime of 0, so we're just going to plug all the x's as 0. So this is going to disappear, and this is going to disappear. So we have e to the negative 1 times 1 over 1 squared. This is just a 1, so you have e to the negative 1, which is 1 over e. It's going to be an irrational number if you plug it in a calculator. Usually just leave it in terms of e, or like even pi. You would just want to leave it in terms of pi. It's cleaner. Let's try doing this. It's asking us to find the equation of the tangent line. So it's a straight line. It's going to be in the form of y equals mx plus b. And they've already given us a point. We need to find m, the slope of the line. What do we do? We're going to find y prime. This is x, so this is f, that's g. What would be y prime? Remember, it's a product rule because you have two different functions multiplying.
So x times e to the power of negative x.
Not x, 1 times e to the power negative x. F prime, right? The derivative of x is 1 plus x as it is, and the derivative, what's the derivative of g here? What's g prime?
E to the power of negative x.
Is that it? Is there any chain rule component to this?
No.
Yes, there is. What's the derivative of negative x?
Negative 1.
Yeah, negative 1. So you have e to the power negative x minus x times e to the power negative x. This is your slope function. Then you need to find your m by plugging in f prime of whatever the x value is into this. So it's going to become e to the negative 1 minus 1 times e to the negative 1. So you get e to the negative 1 minus e to the negative 1. These are like terms. You get a 0. What does that mean? We got a slope of 0 here.
It's a straight line.
Yeah, it means there's a turning point. When the x value is 1 for this function, there is a turning point. Therefore, the equation will just be a horizontal line, right? It's going to be y equals to whatever that value there is, the y value there. Cool? Unless there's something super... So that was for e to the x. E to the x is simple because the derivative is itself. But what if you have something else entirely? Now, these are also exponential functions, but this is not e, right? The base here is not e. So how does that change? It's funny because this one is also very, very similar, but it's a little bit more complicated. One extra step. So if you have anything in this form, right? See this?
Mm-hmm.
Let's say this is a general rubric. A is a constant, a to the f of x. The derivative of this will be itself, okay? It'll be itself times the ln of that constant times the derivative of the exponent, the chain rule. This is the chain rule component. So the difference between e to the f of x and a to the f of x, where a is any number except e, we just got to multiply by ln of a. What does that mean? Let's look at question 1. You have y equals to 5 to the power of x. Y prime is going to be itself times the ln of 5, okay, the natural log of 5, times, well, the derivative of the numerator there, so the exponent is a 1. So it's just 5x times the ln of 5, and that's it. The only difference is you gotta add this ln of a component onto it. Using this idea, what would be the derivative of b? This is the general formula for it. It is going to be itself, right? Look at this. A of f of x, a of f, it just drops as it is. And then you multiply this by the natural log of that number there, the base. So times ln of 5, and then times the chain rule. What's the derivative of the exponent? What's the derivative of 3x minus 2?
3.
3. And there you go. That gives you the derivative of any exponential function. The difference between e and this is just this guy here. Everything else is exactly the same. Cool?
Mm-hmm.
Let's do a word problem where this is used, I guess. This is talking about a population. Populations are modeled using exponential functions. Okay, so they've given us a function where p of t is the number of people and t is the number of years since 1850. Part A, what was the population of this town on January 1st, 1900? How many years have passed from 1850 to 1900?
150.
Quick maths. That was quick maths, but that's the wrong kind of quick maths. Try again. 1850 to 1900.
1,100.
No, I think you're overthinking it. It's 50. No?
Oh,
1900 minus 1850 is 50. Part A is just asking us to find the population when t is 50. 50 years after. Okay, t is the number of years after 18 or since 1850. So if t was 1, it would be the population on Jan 1st, 1851. For part A, all you do is you plug in truck question. Plug T as 50 into the equation. Like that. Cool?
Mhm.
Nothing required. This is a basic question, part A. Part B now, it's asking us for the rate of change. You see, at what rate was the population changing? What are they actually asking us? What does rate of change mean in this context?
You find the derivative.
Yeah, rate of change is the slope. In fact, it's the instantaneous slope, which is the derivative. So we need to find P prime of t. Okay? P prime of t. Want to have a go at this? What is it? Here's the rubric for it. A to the f of x, the derivative is, again, there could be some constant here. It's going to be exact self times the ln of this constant here times the derivative of the exponent. Compare this with this. What is the derivative?
First, you write itself
Yeah, you literally copy paste it, right? I love copy pasting. Then what?
times ln of 50,000.
No, the base. You see, who does the fx belong to? Is 50,000 being raised to the power of t?
No, 0.98.
0.98. Yeah, ln of 0.98. And then times what? The derivative of the exponent, right? Which in this case is 1. So you can just ignore that. So that is the slope function for this. And then we want to find P prime of 50. That'll tell us whether this thing is positive or negative. It's asking us it's decreasing or increasing. You plug this in there. Here's some quick maths for you. You can plug this in a calculator, but a ln of anything less than a 1 is going to be a negative number. So this will never be negative. This is negative. So the final answer will be negative something. So that means the rate of population change is decreasing, okay? It's decreasing at that point in time. Make sense? Here's a question for you. Is the tangent at this point increasing or decreasing?
Increasing.
What about here?
It's increasing.
Okay, now this is gonna be a mouthful, okay? Look at this, look at the terminology. This one is increasing, right? But it's increasing at an increasing rate. What this means is compared this with this, still increasing here, but this one's increasing more. And then if you draw more, it's going to increase more. This one though, it's increasing because it's positive. It's increasing because this tangent line is positive, but it's increasing at a decreasing rate. Now, what does that mean? That means if you compare this with this, you see the slope here was higher. The slope here was higher. The more vertical a line is, the higher its slope, okay? Eventually, it's going to plateau right here. It's going to become 0. So this is increasing at a decreasing rate. Increasing means whether the tangent is going up or down, and the rate, you have to look at the general pattern of where it's headed. Tell me, what is it here?
It's decreasing at a decreasing rate.
Yeah, perfect. Decreasing. And then last thing here. What about this?
Is it the same?
So this is dd, okay? Decreasing at a decreasing rate. This one is decreasing for sure because the tangent is going down. What about the rate? Is it, look at the trend. Is it becoming bigger or smaller? It's becoming more vertical, the tangent line, right? See, we started horizontal and then it started being vertical, vertical, vertical. This is decreasing at an increasing rate. Okay.
Mm-hmm.
Like, what does that mean for real life stuff? You can look at the population basically of like some places like Japan. Japan's population, for the most part, follows this. The growth, it's growing, right? It's
Mm-hmm.
growing, but the growth rate is going down. Okay. The growth rate is going down. And that's one of the solutions to actually overpopulation, because you can't avoid the number of people going up, right? But you can decrease the rate. Same thing with like COVID infections as well. This is basically why there was like lockdowns and stuff, if you remember. Basically to decrease the rate, okay? The number of
Mm-hmm.
infections were probably not going to go down, the total number of infections, but the rate at which it spreads, if you can decrease that, then that's good. Right now, though, the world population is like this, and it's been like this for a very long time. Since science, I guess, because medicine, people didn't, their life expectancy about 200-300 years ago was like 30, 35. But now it's like Canada is like 80 something, 82, pretty sure, something like that. Let's look at this. You have a polynomial function for f, and then you have an exponential function for g. What is the derivative of this? What rule do we use? You got to use the product rule, right? You have two different things.
Mm-hmm.
So what's f prime? Again, this is a simple question. You have f times g. So it's going to become f prime g plus f g prime. What's f prime?
5x to the power of 4.
Yep. What's g? Well, g is as it is. Plus f as it is. What's g prime? So we're trying to find the derivative of this exponential function. Again, it's going to be itself times the ln of that base times the derivative of this guy if there's an exponent. So it's going to be 5 to the power of x as it is times ln of 5. And the chain rule doesn't apply because the derivative of x is just 1.
Mm-hmm.
Here's another use of exponential functions, decay. There's something, well, population as an example of exponential growth, but something like the price of a car is an example of exponential decay. where it falls really quickly. You know what's funny? Like if you go and buy a car, the second you buy it, its price is gonna drop by about $10,000. That would be an example of exponential decay. Okay? Huge
Mm-hmm.
jump, huge jump. But then if you look at this, after a few years though, like the jump is gonna be so small, it's gonna be negligible. So I guess it depends on what you're looking for. It says the percent left after t years is given by this. Okay. When it says half-life, right? It means this happens with like radioactive substances. They lose their mass by irradiation into the atmosphere. So it's like a form of energy. Basically, mass becomes energy. And eventually, if you started off with this, half-life is the time that it takes. Let's say you started with 100 grams. Half-life is the time that it takes for it to become like 50 grams. Exactly half. Okay?
Okay.
In terms of percentage, how much percent is left if it undergoes half-life?
50.
Exactly 50. So here we need to find, this is the percent, so percent is gonna be 0.5. Okay, like that. Or we can even say it's 50. Because this is 100, I guess this is 50. Now we have an exponential equation. How do we solve this for t?
You divide by 100.
Okay, so you get 0.5 is equals to 1.2 to the negative t. Then what?
You do log.
Yeah, so if you remember, if you do log, what do? You take the logs on both sides, right?
Mm-hmm.
So what's gonna happen to the left? What's gonna happen to the right? So you're gonna take logs here, log here. The whole point of using log is that this exponent drops, right? So you have
Uh-huh.
log 0.5 is equals to negative t times log of 1.2. Now what? You divide both sides by log of 1.2, and then you multiply by 1 on both sides, like this, or negative 1, sorry. And that will give you t. Okay?
Okay.
That makes sense or no?
It does.
Is this tricky?
No.
Part B, how fast is the substance decaying? What do you think we need to do? We want to find the rate of change. Again, how fast means the rate at which it's decaying, right?
So you
Again,
find the derivative?
yeah, you want to have a go at it? What's the derivative of this? Again, it's an exponential function. You're going to rewrite as it is, exactly the same.
And then ln of 1.2.
Yeah, what about the chain rule component?
You get a negative 1.
Yeah, you get a negative 1. There you go. And whatever the answer to this was, you're going to plug that back in here as t to find the final answer for part B. Okay?
Mm-hmm.
Is this tell me, what is this? Is this dd, di, ii, id?
dd.
Yeah, exactly. So half-life is dd, decreasing at a decreasing rate. Alrighty, let's call it a day there.
All right, thank you.